Today we'll be talking about the speed of waves on a string. Alright, so we have a string here and we're actually creating a simple harmonic motion and a wave pattern on the string. And the faster this pattern moves depends on the properties of the string and also the tension of the string. And we're going to try to investigate why. The speed at which the wave moves to the right depends on how quickly one particle of the string is accelerated upwards in response to the net pulling force. And remember from Newton's second law, the greater the force or tension in this case, the greater the ability of one particle to pull or accelerate the next. Therefore, the greater the tension, the faster the wave moves on the string. Now let's think of that. The greater one pulls on two, the more force it pulls or tension it pulls on it, the greater it will accelerate it. Therefore, if it accelerates it faster, the overall velocity will be faster. Also, the less massive a particle is, the faster it will accelerate. So if these particles are really light, it will accelerate much quicker and therefore it will move a lot faster. So think of it logically. More force, greater acceleration, greater speed. More mass, the harder will it be to accelerate and therefore less speed. And this can be summarized in this formula, where velocity is equal to the square root of F, which is a force or tension in the string, divided by the mass per unit length of the string. The greater the tension, the greater the speed, and the less mass per unit length you have, the greater the speed. And that's also called what's called linear density. So let's try an example. Transverse waves travel on each string of an electric guitar after the string is plucked. The length of each string between its two fixed ends is 0.628 meters, and the mass on one string is 0.208 grams, and on the other is 3.32 grams, and the tension for both of them is 226 newtons. What we're trying to do is find out what the speeds are on the two strings. So all we do is plug it into the equation and we get our answers. But I want to spend a couple moments looking at this. In this case we kept the tension the same. So the only thing we varied is the mass per unit length. So here, where the mass per unit length or the linear density was small, the speed was really high. And here where the linear density was greater, the speed was lower, which makes sense. As we said here, if the particles are easier to move, the acceleration will be greater, therefore the velocity will be greater. And here the mass was more per unit length, so the speed was slower. And we could also do a problem where we varied the force as well. If you have a greater force or tension, the speed will be higher as well. Alright, let's try another example. Is the speed of a transverse wave on a string the same as the speed at which a particle on the string moves? So is this particle going to move at the same speed as a wave moves? Now the particle will have to move up and down as the wave moves to the right. The answer is no. The particle speed is constantly changing because it's following simple harmonic motion. And it follows the format of the equation that we learned in the last chapter under simple harmonic motion. Meanwhile, the speed of the wave is constant, assuming we don't change any of these variables like the tension of the string or the mass per unit length of the string.